Ahoy me hearties, welcome to Sunday Night Physics with an unorganized university student. In this video I'll explain how we built our motor and more importantly the physics behind why it worked. This week's quote of the week goes to my homeboy Thomas Edison, who said, "To invent you need good imagination and a pile of junk." The aim of this practical was to build a motor from the objects given. These are a battery, an insulated wire, a magnet, and a screw. Initially, to me, these seemed like a pile of junk, hence the quote of the week. But before we dove right into construction, we took a step back and asked ourselves a simple question, this being, what is a motor? The conclusion we drew was that a motor is simply a machine which is powered, in this case by a battery, that supplies motive power for another device with moving parts. To think like a physicist, we must learn to build on fundamental truths. Once we establish what a motor is, by using Sherlock-like deductive reasoning, our motor was built with relative ease. Our train of thought is as follows. Firstly, as the current from the battery is vital for movement to occur, the wire must be connected to at least one end of the battery. In this case, it was the positive end. This wire will supply the current to the moving part of the motor. Secondly, to achieve a maximum amount of motion, a minimum amount of friction must be present. Therefore, the tip of the screw must be in contact with the battery. Intuitively, we assume that this was at the opposite negative end of the battery. Lastly, a spin did not result when the wire was attached to the screw. We assumed that the magnet had to be placed on the head of the screw as we eliminated every other position for the magnet. Once the wire was connected to the magnet, voila, magic. I mean science. Figure 1 depicts an end result of what our motor looks like. Figure 2 is a slow motion video of our motor in action. By counting the amount of times the paper attached to the screw rotated, we were able to track the complete rotations of the magnet. This allowed us to conclude that the magnet rotates approximately 14 times per second, meaning that every minute the magnet rotates. Well, I can only count up to 14, but I'm sure you guys will be able to figure it out. Before advancing on to electromagnetism and why our motor worked, we must develop an understanding of how a magnet works. Essentially, magnets are composed of both a north and a south pole. The north pole will always be attracted to a south pole and repelled by other north poles, and the south pole will always be attracted to the north pole and repelled by other south poles. This attraction and repulsion generates a magnetic field around the magnet, which is the basis of why our motor worked. Some of the observations we made was that the direction of the spin changed if we reorientated the magnet. To track this, we labeled one side of the magnet side alpha and the other side beta. If the tip of the screw was connected to the negative end of the battery and the alpha side of the magnet was joined to the screw's head, then an anti-clockwise motion occurred. Conversely, if the beta side of the magnet was attached, then a clockwise spin would result. After noting this, we became curious if the battery had any influence. To see its effect, we attached the tip of the screw to the positive end instead of the negative end, and if the alpha side of the magnet was connected to the screw's head, it spun clockwise instead of anti-clockwise as we previously mentioned. Similarly, if the beta side was connected, then it spun anti-clockwise. From this we can conclude that both the orientation of the magnet and the battery impacts the direction of the spin. We discovered it acted in this manner due to something called Lorentz force, which some old guy basically described as if a charge moves through a magnetic field at a 90-degree or perpendicular angle, then the direction of the force will result in motion. This follows the right hand rule, which is simply if you took out your right hand, stuck your thumb up, pointed your forefinger forward, and made your second finger perpendicular to the other two, the force applied will be in the direction which your second finger is pointing. Through further research, we discovered that this is known as a homopolar motor. These motors worked because the current applied crosses perpendicularly to the magnetic field. This is also, as we discussed previously, Lorenz's force. But to expand on what we already know, we wondered what would happen if the wire was attached to the bottom of the magnet. This is not perpendicular, this would be parallel to the magnetic force. And upon doing so, we discovered that no spin resulted.